Hello everyone, my name is Jesus Javier Gutierrez and this is my defense presentation for the doctoral degree in electrical and computer engineering at the University of Texas at El Paso under the supervision of Dr. Raymond C. Rumpf and with the Ph.D. committee members Dr. Manchu, Dr. Flores, and Dr. Gonzalez. The title of my dissertation is Independent and Simultaneous Control of Electromagnetic Wave Properties in Self-Collimating Photonic Crystals Using Spatial Variance. This is the outline of the presentation. Here is a summary of the dissertation. The topic is to explore the role of spatial variance for controlling electromagnetic wave properties in self-collimating photonic crystals. The hypothesis is that spatially variant self-collimating photonic crystals will provide a new mechanism to independently and simultaneously control the phase and power of an electromagnetic wave. This will create a new paradigm for controlling light in photonic crystals. And the results were demonstrated by the ability to control the phase and power of an electromagnetic wave in 2D and 3D self-collimating photonic crystals using spatial variance, as well as the arbitrary control of power flow in a fully 3D photonic crystal. The significance of this research is best explained in this picture of an optical system that controls multiple wave properties. First, we have a waveguide band that controls the direction of the wave and steers the beam 90 degrees. Then, the wave goes through a lens that collimates the beam that goes through a birefringent wave plate that changes the polarization of the wave. It goes through a lens again in order to focus the beam and couple it into the waveguide. Now I want to focus your attention to this small area. If we zoom in, we can see that a photonic crystal can do all of these changes at the same time in a tiny fraction of the volume, enabled by spatial variance and self-collimation. Here, a 90-degree bend is obtained by rotating the unit cells. The focusing is enabled by changing the field fraction in the shape of a lens, and the polarization can be controlled by incorporating anisotropy. Combining multiple patterns of spatial variance inside a photonic crystal allows different properties of the wave to be controlled at the same time. This lets us have an unprecedented level of control over the waves inside photonic crystals and potentially unlock new ways to utilize diffraction to control light inside these devices. Now, the research summary is going to be two main points. First is to demonstrate the control of phase and power in self-collimating photonic crystals using spatial variance. Two will be to lay the theoretical and practical foundations to design novel 2D and 3D photonic devices based on diffraction phenomena that can multiplex different functionalities in a single volume. Now I'm going to list my scientific contributions. The first contribution is the decoupling of phase and power in self-collimating photonic crystals using spatial variance. Here you can see that a wave traveling through this photonic crystal, the power follows the direction of the unit cells. However, the phase misaligns with the power vector by entering this green triangle area with thicker unit cells. When the wave exits, phase and power realign again, resulting in a beam steering at the output. The second contribution is the arbitrary control of power flow in 3D self-collimating photonic crystals using spatial variance. Here we see two examples of waves traveling through different lattices, composed of a cubic unit cell and the other using a hexagonal unit cell. You can see that they follow this path, where the arrows point to the input and output phases. This is achieved by changing the orientation of the unit cells as a function of position using spatial variance. The third scientific contribution stems from the need that in order to control multiple wave properties in photonic crystals using spatial variance, the unit cells need to exhibit self-collimating properties over a wide range of frequencies. For this purpose, this quad chart was created that identifies the optimal unit cells both in 2D and 3D and also both with low refractive index and high refractive index that exhibit self-collimating properties over a wide range of frequencies, and I was responsible for identifying the volumetric unit cells. The last, but not least, scientific contribution is the creation of numerous graphics and animations that have helped push the EM Lab's research forward. In particular, I was part of the research team that developed the world's first 3D printed volumetric circuit, as shown in the animation. I helped design the distinctive shape that you see here in this video, as well as the renderings and animations that are now part of publications and press releases, and it is something I am proud of. Preliminary topics. First, I'm going to introduce Maxwell's equations in time domain. First is Gauss's law. Second is Gauss's law for magnetism. Third is Faraday's law. And fourth is Ampere's law. In the absence of electrical charges and sources, the term ρ is dropped in Gauss's law, and the current density is dropped in Ampere's law. In the frequency domain, the time derivatives are replaced by j omega. So now Faraday's law looks like this, and Ampere's law looks like this. We also have a set of two constitutive relationships that relate the physical materials to the electric and magnetic fields. This is the one for the magnetic field, B equals mu h, and for the electric field is D equals epsilon E, where these are the values for permeability of free space to the left and permittivity of free space to the right. Assuming diagonally anisotropic materials, the permittivity and permeability tensors look like this. In the real world, electric and magnetic fields exist in the same place and the same time. However, this is not possible in a discrete grid because it would lead to stability issues in the numerical domain and will be very difficult to implement. It is best practice to stagger the field components in an arrangement called the Yee grid. The Yee grid staggers the electromagnetic fields in a manner that is divergence-free and provides an intuitive and elegant arrangement to approximate the curl equations. An example of this is denoted by the green circle, which denotes the curl of the magnetic field. This animation shows a 3D Yee grid unit cell with its corresponding staggering of the fields in Cartesian space. So in order to calculate derivatives in this discrete space, we can use finite difference approximations. Here's an example how to do it. We want to take the derivative of this function at this point. So the derivative is equal to rise over run. It's going to be the function at the next point minus the function at the previous point, divided by the distance, which in this case is to delta, and it is described by this expression. Now we will derive a finite difference approximation using the Yee grid. We will start with Maxwell's curl equations expanded into its Cartesian components. We will derive the finite difference equation for this expression, and a similar process can be done for the others. For the first component, the derivative of Ez with respect to y is Ez at the next cell minus the Ez at the current cell divided by delta y, which is the length of the Yee cell in the y direction. Here is what it looks like, where I, j, and k represent the indices of the Yee cells in the x, y, and z directions respectively. For the second expression, we have the derivative of Ey with respect to z, and it's the Ey component at the next cell minus the Ey component at the current cell divided by delta z. Here is the full expression for the finite difference approximation for the curl of hx. When we're taking finite difference approximations for a grid, for example this 3x3 grid, we get a large set of equations. Now imagine if we have a grid with hundreds and hundreds of points along many dimensions. We can group all these equations into what is called a finite difference matrix, in which we stored the function values in a column vector. Then our finite difference matrices have ones, zeros, and minus ones representing the finite difference approximations at each point in the grid. The perfectly matched layer, or PML, is a computational construct designed to artificially absorb waves going out of the simulation boundaries. It is used to truncate the computational regions in numerical methods like finite difference frequency domain and time domain, giving the impression that the waves propagate infinitely into space. To achieve this behavior, the PML is required to perfectly absorb scattered waves while actively suppressing reflections at the edges, as shown in the animation. In order to implement the perfectly matched layer, or PML, we need to introduce anisotropy and complex quantities in the constitutive parameters to match the medium impedance, while also introducing loss. A simple and effective method is the uniaxial PML, or UPML, which applies uniaxial anisotropic boundaries. The use of anisotropic materials ensures that the UPML absorbs waves encompassing all polarizations, frequencies, and angles of incidence as shown in the picture. The tensors associated with the UPML are defined in Cartesian coordinates in this tensor S. The UPML quantities are defined as complex materials with a fictitious conductivity and permittivity parameters as a function of position. For best performance, the conductivity terms are defined in a polynomial cubic fashion to ensure that the loss terms increase gradually into the PMLs. The finite difference frequency domain, or FDFD, is a numerical method that calculates the steady-state solution to Maxwell's equations. The FDFD formulation leads to a system of linear equations in matrix form, AX equals B, that does not necessarily scale well in memory use for large problems. However, it is a fast solver and very easy to implement in two-dimensional scattering problems. The next sections will show the formulation and the numerical implementation of the two-dimensional FDFD algorithm. For FDFD, first we incorporate the UPML into Maxwell's curl equations, which is very easy to do in the frequency domain as it's just a multiplication with the permittivity and permeability parameters. Here the curl equations are normalized to the wave number k0, and also the magnetic field is normalized for numerical stability, and we have our parameters which are going to be denoted by the prime symbol as just a multiplication of the permittivity and permeability parameters times the UPML parameters. Now Maxwell's curl equations are expanded into its Cartesian components as shown here, with the UPML already incorporated into the permittivity and permeability parameters, and the coordinates are normalized by the wave number denoted by x prime, y prime, and z prime. Now we can write these equations as finite difference approximations with the components staggered on the Y grid as shown here. Now remember that these 6 equations are written for every single cell, which leads to a very large set of equations. This very large set of equations can be written in matrix form as shown here. Since we are formulating for the two-dimensional case, the propagation of waves is restricted to the xy plane, and the z derivatives are set to 0. Here are the modified Maxwell's equations for the two-dimensional case. This set of equations can be grouped in two uncoupled modes, colored blue and red. The blue set of equations is called the E mode, while the red is called the H mode. For this work, only the E mode will be solved. Now, when solving for E mode, first we solve for Hx in one equation, then we solve for Hy in the other equation, and then we substitute both expressions in the Ez equation. Then we have what is called a matrix equation in the form of Ax equals B, where B equals 0. Now we're ready to incorporate the source that will lead us to a solution for the finite difference frequency domain problem. The introduction of the source is going to be done via the total field scatter field approach as shown in the figure. This approach splits the grid into two different regions: the scattered field, in which only reflected fields appear, and the total field, in which the source is injected and all the fields, both transmitted and reflected, appear. The implementation is done via a masking matrix Q, a matrix with ones and zeros along the main diagonal. They introduce correction terms to the finite difference equations that span the total field scatter field interface. The ones indicate cells in which the scattered field is located, and zeros indicate where the total field is located. The source is now defined as a column vector, and the scattered field region is given by the matrix Q times the column source. The total field region is equal to the identity matrix minus Q times the source. This is a block diagram to implement FDFD. First, we build the device on the grid, then we incorporate the PML parameters on the grid and build the wave matrix A. Then we compute the source by this equation, B equals QA minus AQ times the source. Then we solve the system of equations, and then we post-process for field visualization. The finite difference time domain, or FDTD, is a powerful method that allows the modeling of electromagnetic wave propagation over time. In the computational domain, FDTD problems scale linearly in memory and are easily parallelizable, allowing large-scale simulations to be made in a reasonable amount of time. The formulation will introduce the discretization of Maxwell's equations in the Y grid. the incorporation and conversion of the UPML to the time domain, and the derivation of the update equation that solves for future time steps. The first step to formulate FDTD is to incorporate the UPML into Maxwell's equations. Now we normalize the electric field and electric flux density with these relationships. Then we have our curl equations now with the UPML parameters here, and after arranging some terms, we have these equations. We expand the UPML terms into Maxwell's equations to obtain these 6 expressions along with the constitutive relationships, then we convert them to time domain. For convenience, only one equation will be converted to time domain, and then the rest can be done with a similar approach. So now we have this expression that is going to be converted to the time domain, and for convenience, CEX is denoted to be the curl equation, and then after expanding these terms, we get this equation with 5 terms, and each individual term will be converted to the time domain. The conversion to the time domain is going to be via the use of Fourier transform pairs, specifically these 3. The first one is multiplication by a constant. The second one is the derivative in time, which corresponds to multiplication by j omega. Then the integral, which corresponds to dividing by j omega. After using these transform pairs, we get this expression. Now, this equation, after a very lengthy process of algebra manipulation, discretization of time and space, and solving for the future time step, leads to this final expression for hx at a future time value. We take notice of these terms in square brackets, which do not depend on any field values and can be taken outside of the time loop, calculated beforehand in order to optimize the code for speed. Remember that this is just an expression for hx, and using a similar process we can solve for all the other electromagnetic components. The incorporation of the source in FDTD is also done with the total field scattered field approach. Here we see a 3D FDTD simulation setup with the total field scattered field boundary. The source is traveling along the z-axis and has components in the x and y directions. The total field scattered field approach injects the source in the curl equations as correction terms, only in the total field scattered field boundary, and are independent of the curl equation terms. Here are the correction terms shown in blue for the electric source and also the magnetic source. Here's a block diagram for FDTD. First, we build the device on the grid. Then, we compute the PML parameters on the grid. Now we can compute the update coefficients before entering the time loop. Now in the time loop, we first compute the curl of E. Then we update the H fields from the curl of E. And then we inject the H source with the total field scattered field. Then we compute the curl of H and update the E fields based on the curl of H. Then we inject the E source. After a sufficient number of time steps has passed or the simulation has converged, then we can exit the time loop for post-processing. The last computational technique shown in this work is plane wave expansion method, or PWEM. PWEM is widely used for calculating dispersion bands in periodic structures like photonic crystals, allowing the analysis of phenomena like self-collimation. PWEM is a rigorous method that solves Maxwell's equations in Fourier space by posing an eigenvalue problem, which allows the calculation of modal solutions for inhomogeneous media like photonic crystals given a block wave vector beta. For plane wave expansion method, Maxwell's equations are represented in Fourier space. Fields are represented in Fourier space as a sum of plane waves at different angles and wavelengths. Devices are also represented as the sum of sinusoidal gratings at different angles and periods. To convey this, we will use the complex Fourier series. For 3D periodic functions, the complex Fourier series is defined as this. Now we can write the complex Fourier series also in terms of the reciprocal lattice vectors defined by T1, T2, and T3. Now we will transform one curl equation into Fourier space. Then a similar approach can be done for the rest of the equations. For the left-hand term, this is a Fourier expansion. Taking the derivative with respect to y, we obtain the term at the bottom. For the right-hand term, this is a Fourier expansion, and when we take the derivative with respect to z, the resulting equation is shown at the bottom. And for the right-hand term, the permittivity and the electric field, since there are multiplication in Fourier space, they become a convolution. Now, putting all of the terms together, we get this big expression, which corresponds with one term corresponding to a triple summation inside a triple summation. This equation needs to be satisfied for each combination of P, Q, and R. Based on this, we can rewrite this equation as follows. Here are all of Maxwell's equations represented in Fourier space. Remember that we need to write this set of 6 equations for each and every combination of PQR, which leads to a large set of equations. These large set of equations can be written in matrix form as follows. Where the k terms are diagonal matrices containing all the wave vector components along the main diagonal, U and S correspond to the magnetic and electric field components respectively, and they contain the amplitudes of each spatial harmonic in the expansion, and the terms in double brackets pertaining to the permittivity and permeability values correspond to convolution matrices. These 6 equations can be written in block matrix form as follows, and they can be written in their compact form. For the PWEM formulation, we start with Maxwell's equations in their compact form, we solve for the magnetic field in the second equation, and then we substitute it into the first equation. Then we have a generalized 3D eigenvalue problem in which our unknown field quantities are the electric fields denoted by S, and our eigenvalues are our k-naught squares. What we're going to do with the PWEM algorithm is we're going to feed it block wave vectors or betas, and we're going to solve the eigenvalue problem for each beta in order to obtain the eigenvalues or solutions to Maxwell's equations in periodic media like photonic crystals. This is the block diagram for the PWEM algorithm. First, we build the device. Then, we compute the convolution matrices based on the device. Now, we compute the list of block wave vectors beta to solve the eigenvalue problem. Then, we enter the beta loop, in which we build the eigenvalue problem, solve it, then scale the eigenvalue, because as we remember it was k-naught squared, and then we do that for each and every beta. After we finish iterating each and every beta, then we can exit the loop to enter post-processing. Now I will talk about photonic crystals. Photonic crystals are periodic structures that control electromagnetic waves in an analogous manner to semiconductors controlling the flow of electrons. Photonic crystals are macroscopic media, generally composed of low-loss dielectrics, and the periodic potential for electrons in semiconductors is replaced by a periodic refractive index. Photonic crystals can exist in 1 dimension, 2 dimensions, or 3 dimensions. In these devices, phenomena like band gaps and dispersion are extensively studied for their many applications in controlling electromagnetic waves. In this work, we're going to focus only on the dispersion phenomena, which refers to the propagation characteristics of the lattice depending on the light's wavelength, direction, and/or polarization. The derivation of Maxwell's equations for photonic crystals is straightforward. First, we start with Maxwell's curl equations with the constitutive relationships already incorporated. Then, we solve for the magnetic field in the curl of the electric field. Then, we substitute that expression into the curl of the magnetic field, and we obtain this. According to Bloch's theorem, electromagnetic fields inside periodic media like photonic crystals take the same symmetry and periodicity as their host. Then, the solution to the previous equation has this form, where beta is the Bloch wave vector. We substitute this expression into the wave equation and we obtain this. This is an eigenvalue problem. These problems have discrete solutions or eigenfrequencies and are orthogonal from each other. This means that in periodic structures such as photonic crystals, electromagnetic waves only exist at discrete modes called Bloch modes. Based on this theorem, linear combinations of Bloch modes are also solutions inside photonic crystals. The solutions to the eigenvalue problem described before are discrete modes that are allowed to propagate in photonic crystals given a Bloch wave vector beta. Through the use of plane wave expansion method by iterating over the full range of betas, the eigenfrequencies can be plotted in the full Brillouin zone. The eigenvalues start to group on surfaces called dispersion bands, as you can see in the animation. These dispersion bands are useful to quantify dispersion behavior in photonic crystals. From the dispersion bands, equifrequency contours can be obtained by slicing a band with a plane at a fixed frequency height, as shown in figure A. Then we can look at the intersections, as shown in figure B. These equifrequency contours can be used to predict the relationship between the Poynting vector P, which describes the direction that power advances in the lattice, and the direction of the phase profile, which is given by beta, as shown in figure C. The Bloch wave vector beta is drawn from the origin of the Brillouin zone to the contour of interest, and the Poynting vector is drawn from the tip of the Bloch wave vector in a direction normal to the equifrequency contour. To understand why the Poynting vector is perpendicular to the contours, we will make use of a parameter called group velocity, and we will derive an expression for it in terms of the dispersion relation. The group velocity is the speed and direction in which the envelope of a wave's amplitude propagates, and it is collinear with the Poynting vector. By definition, group velocity applies to a wave composed of more than one frequency. By use of trigonometric identities, this expression can be rewritten as a product of two waves. This equation can be further rewritten in terms of the center frequency omega c and bandwidths delta k and delta omega. We can interpret this expression as a sine wave with frequency omega c that is modulated by a cosine function. This modulation term is effectively identified as the envelope of a wave, and the speed of it at which it moves is constant, which makes the argument inside the cosine equal to 0. Now, with the argument inside the cosine equal to 0, we can take the derivative of the argument to have an expression in terms of velocity. If we take the limit of the delta frequency omega and the delta wave number k approach 0, we obtain that the group velocity is equal to the derivative of the frequency with respect to k. If we generalize this expression to more than one dimension, we obtain that the group velocity is the gradient of omega k, where this is the dispersion relation. Since the Poynting vector and the group velocity vector share the same vector and are collinear to each other, this gradient expression proves that the Poynting vector is perpendicular to the equifrequency contours. In periodic structures like photonic crystals, equifrequency contours can have different shapes depending on the frequency of the source, as well as the shape of the unit cell and the materials. Figure A has an equifrequency contour in the shape of a circle, and so beta and p travel along the same direction. Figure B, equifrequency contour has a pincushion shape, and so beta and p travel in different directions. Figure C has an equifrequency contour in the shape of a square, and now beta and p also travel in different directions, but also p travels along the same direction over a wide range of betas. This is called self-collimation. It is then very important to understand that when a wave travels through a photonic crystal, the corresponding phase beta and power p are effectively uncoupled and can take different directions based on the shape of the equifrequency contours. If aspects of the unit cell, like material composition, field fraction, orientation, among others, are changed as a function of position inside the photonic crystal, the equifrequency contours are effectively engineered, and the phase and power can be controlled independently and at the same time throughout the photonic crystal. This figure describes the behavior of a wave entering from a homogeneous medium with equifrequency shape of a circle to a photonic crystal with negative dispersion or a pincushion shape, showing different directions of phase and power among the different mediums. As explained before, when a wave enters a photonic crystal and the equifrequency contour exhibits a flat line over a range of betas, the wave is self-collimated, and the power will propagate in a direction normal to the contour. The wave is forced to travel in a single direction without spreading or diffracting, as you can see in the figure, and can be independent of the angle of incidence. In two-dimensional photonic crystals, the dispersion surfaces were open along the beta x and beta y axis, and the equifrequency contours describing self-collimation were flat lines. Now, in three-dimensional crystals, the dispersion behavior is now in the shape of closed surfaces, as you can see in this animation, and the flat lines are now replaced by equifrequency surfaces. Now we move on to spatial variance. What is spatial variance? Spatial variance is an algorithm that introduces geometrical changes to a periodic lattice in a manner that is smooth, continuous, and free of unintentional defects. To better explain what I just said, I'm going to use an example. Here we have a simple periodic lattice. Now, imagine that I want to take this side, grab the lattice by this side, and then try to move it to this side, effectively making a 90-degree bend. Here is what a conventional spatial transform would look like to implement a 90-degree bend. You can see that the arrow flows in the direction that is intended. However, the lattice is very compressed in this region and it is stretched in this region. This effectively destroys the electromagnetic properties of the lattice. With use of the spatial variance algorithm, we have this. Now you can see that there is no compression or stretch, and the bend is preserved, and the unit cell shape is also preserved. In order to formulate the spatial variance algorithm, we need to understand the concept of grating vectors. Grating vectors are functions that are analogous to electromagnetic plane waves in the sense that they travel along the same direction while accumulating phase. The grating vector function is defined by this expression, where k is a vector described by the magnitude and the vector r is a vector position. However, the grating vector definition falls when representing some functions, like a chirped grating. So we need to introduce an intermediate parameter called the grating phase. This relationship between the grating vector and the grating phase is shown here, which states that the gradient of the grating phase is defined by the k vector. This is the equation that we will need to solve for the spatial variance algorithm. Now we solve for the grating phase. The equation is expanded into its Cartesian components. They can be rewritten in matrix form as follows. This is an overdetermined system in which there are more equations than unknowns. Therefore, the grating phase is solved in the term of least squares as follows. Now that we know how to solve for the grating phase, we can define the grating vector to be this expression and obtain the grating phase. Here we can see that there are many parameters, like the period, the orientation, and also a binary threshold function. Here is a list of spatially variant inputs to solve for the grating phase. Here is a grating with no spatial variance. If we spatially vary the period, we obtain this. If we spatially vary the orientation for a 90-degree bend, we have this. We can also spatially vary the field factor with the binary threshold function. Finally, we can combine all of these spatial variances at once. The ability to do this is key to the research presented here, as different spatial variances allow for control of different wave properties, leading to new mechanisms of diffraction optics that can multiplex different functionalities in a photonic crystal. For periodic devices like photonic crystals, we can take the baseline unit cell and decompose it into a series of planar gratings, as you can see in this figure of a 3D unit cell, in which every block is a planar grating that overlaps and adds to reconstruct the original cell. Then, for each planar grating, we apply the spatial variance algorithm and add the solution to the overall list of planar gratings to construct the spatially variant lattice. Here is a quick block diagram describing the spatially variant lattice algorithm. First, we define the input maps such as period, orientation, and field fraction. Then, we create the unit cell and decompose it into its set of planar gratings. Then, for each spatial harmonic, we compute the grating phase and add it to the overall lattice. Then, we apply the threshold function with field fraction to obtain the binary grating. Solving for the grating phase in matrix form is computationally expensive in terms of memory requirements, especially when working with 3D lattices. For this purpose, an iterative formulation of the algorithm was developed, which paves a practical way to introduce spatial variance in 3D photonic crystals by reducing memory requirements. The already known grating phase equation is expanded into its Cartesian components. Then, a general expression to obtain a new grating phase value from the previous one is derived by calculating the grating phase across x, y, and z. This approach is done in an iterative manner until convergence is reached by looking at the difference of the new grating phase with respect to the old grating phase. State of the art. There's been some examples that control power flow in self-collimating photonic crystals. This is a photonic crystal with a parallelogram lattice, capable of bending a self-collimated wave at different angles and has also partial bandgap reflection. However, the changes are very gradual and require many wavelengths to implement the bending. This is a crescent-shaped photonic crystal, where the unit cell has reduced symmetry and its dispersion properties are very sensitive to rotation. By rotating the unit cells in different regions, the dispersion relation is changed, and it very gradually and weakly controls the power flow of an incoming wave. This is an example of control of power flow of sound waves in self-collimating photonic crystals. This is a lattice with rectangular inclusions that are rotated as a function of position. The propagation direction of the beam is manipulated by the rotation angle of the inclusions. This approach is limited because the rotation must be very gradual and does not rotate the lattice unit cells like the spatial variance algorithm does, only rotates the inclusions. Here is an example of phase control in self-collimating photonic crystals. This is a Mach-Zehnder demultiplexer consisting of two beam splitters and two air gap mirrors. The splitter forces the wave to travel along different paths, one short and one long path, and when they meet at the other side, they either constructively or destructively interfere with each other, changing the exit port. The system is big, complex, and with many stages to control the phase. It also requires the introduction of defects, which can reduce the efficiency of the system by introducing unwanted reflections, and can change the overall shape of the lattice, which invariably affects the shape of the equifrequency contours. And only so many changes can be introduced before the dispersion surfaces lose the flat contours required for self-collimation. Lastly, all of these works presented do not intentionally control both phase and power independently and at the same time. There's also been some efforts and ideas to control power flow in 3D self-collimating photonic crystals. This is a conceptual rendering of an optoelectronic device with a buried photonic crystal underneath for optical routing. The optical routing is based on the self-collimation effect as well as angled mirrors. This is another example of control of power flow. This is a simulation of a self-collimating photonic crystal with a body-centered cubic unit cell incorporating a splitter and also a double bend with the use of mirrors by truncating the lattice in certain regions. The work presented in the previous slide and this one are either conceptual renderings or simulations using approximate methods, and do not offer a clear methodology on how these devices can be designed in order to be implemented in real life. It also has the same problem of introducing rift defects in the lattice, which can invariably affect the overall shape of the equifrequency contours for self-collimation, and can reduce the overall efficiency of the device by introducing unwanted reflections. Now I'm going to present my research. First, I'm going to show the decoupling of phase and power in self-collimating photonic crystals using spatial variance. I will first present the two-dimensional case. In order to control phase and power in self-collimating photonic crystals using spatial variance, it is desired that a unit cell exhibits self-collimating behavior over a wide range of frequencies and vector angles. This broadband behavior ensures that the unit cell is robust enough to vary its geometrical properties without losing its self-collimation. A suitable unit cell was found where a hybrid photonic crystal consisting of rods and circles was shown to possess flat equifrequency contours over a wide range of vectors in the fourth band. With this unit cell, a spatially variant photonic crystal was designed that manipulates phase and power independently and at the same time, as shown in this figure. When a wave propagates through the photonic crystal, the power flows in a direction normal to the equifrequency contours, which is the direction parallel to the rods. Inside the green triangle highlight, the rods are thickened slightly, while also being rotated, as seen in the middle inset. This change does not erase the self-collimating effect because the basic shape of the unit cell is preserved. However, due to the field fraction change, the direction the phase advances misaligns with the direction the power advances, as shown here. The effective refractive index of the material changes as a function of position and shifts the equifrequency contours of the unit cell, while still preserving the flatness for self-collimation. When the wave exits the crystal and enters a homogeneous medium like air, phase and power realign again, resulting in a beam steer at the output. 6 spatially variant photonic crystals were simulated with different combinations of spatial variance. This figure shows the angle orientation map of the unit cells in degrees. These two figures show the spatially variant field fraction maps. The maps show the thick and thin regions of the rods throughout the lattice. The left image shows the positive field fraction map with thicker rods in the triangle region, and the right image shows the negative field fraction map with thinner rods in the triangle region. These first three simulations show straight lattices with no spatially variant orientation, but with spatially variant field fraction of the waveguide rods. Different output beams were observed depending on how the field fraction was spatially varied. The middle simulation shows the straight lattice with no modifications to the field fraction. The left simulation shows the lattice with thinner rods highlighted in the red region, while the right simulation shows thicker rods in the green region. This uneven field fraction distribution causes a phase gradient in the cross-section of the beam that makes phase in parts of the self-collimated beam advance either faster or slower, creating a beam steering effect at the output. The lattice with no field fraction modification exhibited a straight output beam as expected. In the left lattice, the wave accumulates more phase in the left side of the beam than the right side. This uneven field fraction distribution causes a misalignment of the block wave vector and the pointing vector, steering the beam to the left. In the right lattice, the thicker rods in the green region makes the wave accumulate more phase in the right side of the beam, steering it to the right on the output. These last three lattices had the orientation spatially varied in addition to the field fraction. In the middle simulation, field fraction is not adjusted, and so the lattice exhibits a straight output beam. The left lattice has the rods thinned in the red region and shows the output beam steering to the left. The right lattice has the rods thickened in the green region and shows the output beam steered to the right. This is the same beam steering effect observed in the first three lattices, which were straight. These videos show finite difference time domain simulations of the last three lattices showing spatially varying orientation and field fraction. Notice the beam steering effect in the left lattice and the right lattice. In order to extend the phase and power control of electromagnetic waves to 3D photonic crystals, a suitable unit cell is needed, just like the two-dimensional case. A promising unit cell was found, with its dimensions shown in the left figure and its isosurfaces shown in the right figure. This 2D hexagonal unit cell exhibits out-of-plane self-collimating propagation over a wide range of frequencies. However, this promising unit cell has some problems. The first one is diffraction, which leads to multiple beams in different directions exiting the lattice, which is unwanted to control phase and power. It is desired for the beam to focus all the power into a single mode beam that can be easily controlled using spatial variance. Another potential concern is that multiple bands show flat surfaces in the same frequency regions, leading to multiple modes being excited at the same time. This is called band degeneracy and requires further research in possible effects when applying the spatially variant lattice algorithm. The last problem arises with the non-trivial problem of reflection. Given that the lattice has high refractive index, there are significant reflections that occur at the interface and at the end of the lattice. The 2D lattice shown in the previous case had incorporated anti-reflection gratings that greatly improved transmission efficiency. Anti-reflection structures must be designed for this unit cell in order to continue further research of controlling electromagnetic wave properties. With the problems presented in the hexagonal unit cell, this work will show that even a simple cubic 3D unit cell can show the decoupling of phase and power in 3 dimensions. A lattice can be designed with a lower refractive index to avoid significant reflections at the interface and has a slight diffraction. At the image to the left, you can see the analog cubic cell, which is the superposition of 3 analog orthogonal gratings. At the right image, image B, you can see the binary cubic unit cell after applying a binary threshold operation. This is a 3D picture of the cubic unit cell after applying a binary threshold operation to the analog unit cell. These are the isosurfaces of the binary cubic unit cell in the third band, calculated using the plane wave expansion method. The red highlighted isosurface corresponds to the normalized frequency omega n equals 0.725, which exhibits flat faces that correspond to self-collimation properties. This is the map for the spatially variant orientation of the cubic lattice, which is the same as the two-dimensional case. Two radial field fraction maps were created to change the phase of the wave and steer the beam at the output. These maps change the threshold value of the analog cubic unit cell as a function of position. The left one is generated with negative or subtractive field fraction, in which the threshold value is higher than the original gamma, to create thinner unit cells near the radial origin. The map on the right was generated with positive or additive field fraction, in which the threshold value is lower than the original gamma near the radial origin, producing thinner unit cells in that region. It is worth noting that these two maps are different than the two-dimensional case using triangular regions, but they work in the same manner to modify the phase of the wave and steer the beam when it exits. In the positive radial field fraction map, when the wave travels in the thicker unit cells region, the wave experiences a higher effective index and phase advances more slowly. In the negative field fraction map, when the wave travels in the thinner unit cells region, the wave experiences a lower effective index and phase advances more quickly. The change of field fraction in both cases is subtle enough to warrant the phase behavior of the wave when it exits, while keeping the isosurfaces from changing too much from the ideal flat surfaces needed for self-collimation. I will show the results of the work. But first, I want to show a graphical representation of the 3D finite difference time domain simulation setup. The simulations will show a single slice from a lattice with dimensions 20A by 20A by 1A, but with periodic boundary conditions along the z-axis, effectively simulating an infinitely long lattice along the z direction. With that said, these are the three lattices with the same spatially variant orientation but different field fraction maps simulated with 3D FDTD. These are screenshots of the steady-state field showing a single slice of a 3D lattice. Left and right simulations had negative and positive field fraction maps respectively, while the middle lattice has a constant field fraction. To measure the amount of phase control inside the devices, the exit beam angle was measured. A vertical line crossing through the middle of the exiting beam was drawn, and the wavefront line was identified. A line perpendicular to the wavefront was calculated and placed so that it intersected the vertical line. The beam angle was then measured from the vertical line to the line perpendicular to the wavefront. The left lattice showed a beam angle of 34.66 degrees. The middle lattice showed an angle of 31.37 degrees, and the right lattice an angle of 27.52 degrees. The simulations are not very clean and show some unwanted scattering, because the unit cell is not a good self-collimator, as it was in the previous case of the two-dimensional lattice. Even with this unit cell showing limited self-collimating behavior, the lattice still shows phase and power control. The conclusion of this section is that it demonstrated the design and simulation of 2D and 3D self-collimating photonic crystals to control both the wave phase profile and direction of power independently and at the same time. The 2D case used a broadband collimator, and its power and phase control is clearly visible by the simulations showing the beam steering. The 3-dimensional case, even though it used a simple cubic unit cell with limited self-collimating behavior, the beam still demonstrated some phase and power control by showing subtle beam steering behavior at the exit. Combining multiple patterns of spatial variance allows different properties of the wave to be controlled at the same time, potentially unlocking new ways to utilize diffraction to control light inside these devices. Now this section will show the arbitrary control of power flow in 3D self-collimating photonic crystals using spatial variance. To date, there have been successful approaches that incorporate spatial variance in photonic crystals, both in simulations and experimentally. Spatial variance has also been successfully introduced in self-collimating photonic crystals to control multiple aspects of an electromagnetic wave like phase and power, as described in the section before. However, the spatial variance implemented in these works has been either in planar photonic crystals or implemented in 2 dimensions using 3D unit cells with layers stacked on top of one another, as shown in the figure. An advancement in the implementation of an iterative spatially variant lattice algorithm as described before, makes it practical to generate fully 3D spatially variant photonic crystals. To demonstrate this advancement, in this section we design and simulate a fully 3D photonic crystal that contains 2 consecutive bands in different planes. In this research, the vector field is generated by drawing a line path which defines the desired path of the electromagnetic wave, which in this case will be a double bend in 2 orthogonal planes. Then, a vector field is created from that line that defines the k-vector functions to be fed into the spatially variant lattice algorithm. The line path and its generated vector field are shown in these figures. 2 lattices were generated with the iterative spatially variant lattice algorithm using 2 different unit cells, as shown in these figures. The first one on the left is a simple cubic unit cell, which was used to prove the first spatially variant photonic crystal in the self-collimating regime. The second lattice uses a hexagonal unit cell that exhibits broadband out-of-plane self-collimation, with the original radius changed to r equals 0.40 b, where b is the lattice constant. The final lattices generated from the iterative spatially variant lattice algorithm are shown in these figures. The left figure shows the lattice generated by the cubic unit cell with dimensions 20A by 20A by 20A, where A is the lattice constant. The right figure shows the lattice generated by the hexagonal unit cell with dimensions 12B by 12B by 12B, where B is the lattice constant. The arrows shows the input and output phases. 3D FDTD simulations were done using the XFDTD software. The source is a single frequency beam, vertically polarized and impinging in the input phase here. The beam inside the lattice is expected to follow the orientation of the unit cells defined by the initial line path and exits the lattice in the output phase here. This animation corresponds to the lattice with the cubic unit cell and has some unwanted scattering in some regions, like here and here. There are two main reasons as to why this may happen. The first reason is that the cubic unit cell is not optimal for self-collimation and has a limited range of acceptance angles or field of view in which a wave can self-collimate. The waves outside this field of view will scatter to different directions and will not follow the path of self-collimation. The second reason is that the vector field fed into the spatially variant lattice algorithm is not enforcing the other two axes perpendicular to the path of self-collimation, and thus the unit cell orientation is not strictly enforced. This limits the field of view of the cubic unit cell, leading to more unwanted scattering. This is the 3D FDTD simulation for the lattice with the hexagonal unit cell. This is the input phase of the beam. It follows the curvature and then exits at the output phase here. Notice that this beam has minimal scattering and clearly follows the double band path as opposed to the cubic unit cell. This is because this unit cell is actually optimal for self-collimation. In conclusion, a new iterative spatial variance algorithm was implemented to produce a three-dimensional spatially variant photonic crystal. This device incorporated a double band in two orthogonal planes to control the power flow of an incident beam. Simulations showed two lattices with different unit cells, one being a cubic unit cell with a narrow field of view for self-collimation, and the other being a hexagonal unit cell with broadband self-collimation properties. The development of this algorithm paves the way to develop a practical workflow to create spatially variant photonic crystals that can arbitrarily control the flow of power. Future work with this algorithm will include the simultaneous change of many geometrical properties besides orientation. Now for the conclusion. In summary, the work presented in this dissertation developed new ways to control electromagnetic wave properties in spatially varying photonic crystals. First, it demonstrated the ability to control the phase and power of an electromagnetic wave in 2D and 3D self-collimating photonic crystals using spatial variance by controlling the field fraction and the orientation of the unit cells to control the phase and power of an electromagnetic wave, respectively. Second, it demonstrated the implementation of a fully 3D spatially variant photonic crystal that showed arbitrary control of power flow by changing the orientation of the unit cells with a double bend by means of a novel iterative spatially variant lattice algorithm. Future work for control of power flow in 3D self-collimating photonic crystals is the generation of not just one line path but multiple line paths that can control multiple beams at once throughout the same volume, which can lead to the radical miniaturization of optical devices. One aspect of electromagnetic waves that is of great interest for future work is polarization. This aspect has yet to be considered by the spatially variant lattice algorithm. The first observations of polarization effects were recorded where a spatially variant photonic crystal was measured experimentally at optical frequencies with different wave polarizations. The vertical polarization, as expected, followed the bend, while the horizontal polarization did not follow the bend and exited on the opposite phase. At the time, this was attributed to the fabrication process, producing an imperfect non-cubic unit cell that introduced birefringence. It was thought that this caused the wave to behave differently with both polarizations. However, a recent 3D FDTD simulation, shown in this figure, showed the same behavior with a horizontally polarized wave impinging on a band with a perfectly cubic unit cell. The wavelength, beam width, band, and materials were identical to the simulations. The beam still does not follow the band curvature. discarding the previously held belief that the different polarization behavior arose due to the fabrication process of the lattice, and points to a more fundamental behavior that requires a deeper level of understanding beyond the scope of this exploratory research. It seems that a polarization parallel to the spatially variant photonic crystal may not be rotating alongside the band like the vertical polarization, and may point to the introduction of spatial variance might be causing this behavior. A small amount of energy is still observed to exit in the desired direction of the band, but this is speculated to be Bragg scattering and not self-collimation directly. For acknowledgements, I'd like to thank my family for their unconditional love and support. To Dr. Raymond C. Rumpf, or Ruthless Rumpf, the best advisor ever. Thank you to all my co-workers in the EM lab. Thank you very much to my first mentor, Dr. Joseph Perlusi, to the Schellinger Fellowship for funding my graduate research through all these years, to Dr. Velez Reyes for his continued support over the years, to all the electrical engineering department staff, especially Priscilla Carrasco, and last but not least, thank you to my defense committee for their time and valuable input in this work. And now, here is a list of my publications and presentations.